Hello and welcome to another video. On the board are two different questions. The first question is a question about projectile motion, and question two is another question, which is a question about what we call Hooke's law. Yeah, this is a question about Hooke's law, and these are 2010 WAEC Section B Part 1, Question 1 and Question 2 Theory Exam questions. All right, so now the first question, we have that a stone is projected vertically upward with a speed of 30 meters per second from the top of a tower of height 50 meters, neglecting air resistance. Determine the maximum height it reached from the ground. So we are given the value of g, okay, which is acceleration due to gravity, to be equals to 10 meters per second squared. Okay, now of course, in this question, we are not given the launched angle, also known as angle of projection. Okay, so in this case, because we are not given the launched angle, let me draw the diagram. So what we'll do is, first, we need to understand that according to the question, we have a tower. Okay, let's say this is the tower. This is the tower. So a stone is projected vertically upward, okay, with a speed of 30 meters per second from the top of a tower of height. So the height of the tower, let me represent height of tower with h subscript t. So we have height of tower to be 50 meters. So, and we know that when an object is thrown vertically upward or is projected into the air, okay, it will move in a curved path or parabolic path, okay, with the horizontal velocity remaining constant, while the vertical velocity, okay, will be changing due to what? Gravity. So which means the motion of an object which is launched into the air or projected into the air under the influence of gravity by following a curved path in the air as it moves, okay, is what we call projectile motion. So which means any freely projected object which moves under the combined action of horizontal and vertical velocity is what we call projectile motion. So in this case, when the stone is projected upward, okay, it will trace some path in the air as it moves, and then fall back to the ground level. Now the height for which the stone, okay, is projected, okay, this is the height for which the stone is projected because the stone is projected vertically upward with a speed of 30 meters per second, okay, from the top of a tower. So the height of the stone is hs, h subscript s. So we have, let's h subscript s equals to height of stone. Now also we know that height of tower, that will be 50 meters, okay, that is from the top of the tower to the what? To the ground level, okay. So we have h subscript t to be what? Height of tower. So this is height of tower, which is 50 meters. And let's not forget that we are given the what? The velocity of projection, which is 30 meters per second. And also we are given acceleration due to gravity. That's g, okay, lowercase letter g, and that is equals to 10 meters per second squared. All right, now our task is to determine the maximum height it reached from the ground. So which means now when we know the value of h subscript s, then we are going to add it to the value of the what? The height of the tower, and that will give us the height reached, okay, by the stone from the what? From the ground. That is the maximum height reached by the stone from the ground. In this case, we are not giving angle of projection, also known as a launched angle. All right, so let's look at what we have here. So we have h, okay, and we also, that is h subscript s, which is height of stone. So let's calculate height of stone. Now we know that when the stone, reaches this point, okay, for every object existing in the Earth gravitational field, when the object reaches the maximum height, or it reaches a point in the what in the Earth gravitational field, the motion will be what interrupted, and the body will what will return back to the ground level. That is, it will fall, it will gradually fall back to the ground level. So in this case, the value of v, which is vertical final vertical velocity, will be equals to 0. Okay, so where the parabola, okay, where the parabola, okay, is flat. Let me put it this way ahead. So the value of v, okay, will always be equals to 0. So when v is equals to 0, now we're going to use one of the equations of kinematics. Here we have h subscript s, height. Okay, we know the value of u, and we also know the value of acceleration due to gravity. So we're going to use the equation connecting initial final velocity, then height of the stone with what? Acceleration due to gravity. And let's not forget that for vertical motion, the value of g will be what? Negative. All right, so in this case, we'll be using the formula v squared equals to u squared negative 2h subscript s, height of stone. Remember, we want to calculate the height of the stone. So when we know the height of the stone, then we're going to add the value to that of the tower to what? To calculate, to be able to what? To determine the maximum height the stone reached from the ground. So in this case, this is 0. So we have u is 30. So we have 30 squared, 2 multiplied by 10, multiplied by h subscript s. So this will be 900 equals to 20 hs. So if you divide both sides by 20, in this case, so we have h subscript s to be equals to 45 meters. So this is the height of the stone. Okay. Now, let's now calculate maximum height reached. Okay, maximum height reached. Maximum height reached by the stone, okay, from the ground. From the ground. So that will be h max, and that will be equals to height of stone plus height of tower. So h max will be equals to height of stone, which is 45, okay, plus 50, okay, plus 50, and this will be equals to 95 meters. So the maximum height reached by the stone from the ground is 95 meters. Okay, so that's question number 1. Now, number 2, solution to question 2. All right, so question 2, like I said, this is a question about what we call Hooke's law. When we say Hooke's law states that strain is proportional to stress producing strain, provided that the elastic limit is not exceeded. Okay, when we have the ratio of what we call the tensile stress to the tensile strain, we have what we call Young modulus. That's in the case of Young modulus. But in this case, of course, we have a force of 40 Newton is applied at the free end of a wire fixed at one end to produce an extension of 0.24 millimeters. So let me write extension. We have extension, which is E, to be 0.24 millimeters. 0.24 millimeters. Okay, then we're also giving the force, okay, the force of 40 Newton. So this is 40 Newton. Okay, now if the original length and diameter of the wire are 3 meters and 2.0 millimeters respectively, we're asked to calculate the stress on the wire. Stress is the force that is applied normally to the surface of an object. That is stress, just like the force acting normally per unit cross-sectional area of the surface of a material. So the force applied normal to the surface of an object is what we call stress. So now we have the original length. The original length is given to be 3 meters. Okay, then we're also giving the diameter. We're giving the diameter. The diameter is given to be 2 millimeters. So for 2 millimeters, this will be 2 times 10 raised to the power of minus 3 meters. Okay, minus 3 meters. So that's the diameter. So the first question is for us to calculate stress in the wire. So stress, we want to calculate the value of stress. So like I said, stress will be force over area. Now, what is the area? Area in this case will be pi, let me use pi r squared. Now, because radius, we are giving the diameter to be 2 times 10 raised to the power of minus 3. So if you divide the diameter by 2, that will be, this will be 1 times 10 raised to the power of minus 3. So now the area will be pi 1 times 10 raised to the power of minus 3 squared. So that this will be 3.142, which is the value of pi. Okay, value of pi is 3.142. Then multiply by 10 raised to the power of minus 6 meters squared. Minus 6 meters squared. So the stress will now be, let's not forget that force is 40 Newton. So this will be 40 divided by 3.142 multiplied by 10 raised to the power of minus 6. And this will be in Pascal. Okay, 1 Newton per square meter is 1 Pascal. Okay, so let's get the value of 40. Okay, divided by 3.142. Okay, that will be 12.73. So this is 12, okay, 0.73. 12.73, then times 10 raised to the power of 6. So this will be 12.7 times 10 raised to the power of 10 raised to the power of 7 Pascal. So this is the stress. That's the stress in the wire. Now, second question is for us to calculate the strain in the wire. Strain in the wire. Now, strain can be represented with epsilon. Okay. Now, strain. When we say strain, strain measures the fractional deformation produced in the wire. Okay, produced in the wire when it is subjected to a set of deforming force, and that's why it can be measured as the ratio of extension to what? Original length. So in this case, strain will be the ratio of extension to what? Original length, which is extension divided by what? Original length. And let's not forget that strain, beg your pardon, strain is a what? Is a dimensionless quantity. That is, it has no unit. All right. So in this case, we know that extension is 0.24 millimeters. Okay. Then the original length is 3 meters, which is what we have here. So then we have strain to be 2.4 times 10 raised to the power of minus, because this is a 2.4 times 10 raised to the power of minus 10 raised to the power minus 3 is milli. Okay, so in this case, this is going to be minus 4 meters. Okay, so that is the extension. So that strain will be equals to 2.4 multiplied by 10 raised to the power of minus 4 meters divided by 3 meters. So that this will be 0.8 times 10 raised to the power of minus 4. And this will be 8.0 times 10 raised to the power of negative 5. So this is the strain in the wire, which is the fractional deformation produced in the wire. Okay, when the wire is subjected to a set of deforming force, and that is the ratio of extension to what? Original length. For those of you preparing for WAEC exam, the noblest pleasure is the joy of understanding. Bye bye.